Hello everyone, my name is Yiqiang Zhang, and I'm from Alibaba Cloud Database Department. I'm a software engineer. Today I want to talk to you about the work we are doing for the next generation of connected database. That's the PolarDB serverless. My talk today will be divided into three parts. First of all, let's talk about the current challenge of the connected database. And in the second part, we will going to introduce the design and the optimization of the PolarDB serverless. Finally, I will show you the benchmark results in all aspects of the PolarDB serverless. Now, let's start the first part. At present, major cloud vendors such as the AWS, Azure, and also Alibaba Cloud all provide relational database service. As the figure listed on the right side, there are three typical architectures for cloud database. The first is the normalized machine. The second is the virtual machine with remote disk. And the third is the shared storage architecture. Although these architectures are widely used, they still have limitations and challenges. Let's see the monolithic first. Its CPU, memory, and storage are all coupled. For the shared storage architecture, although its storage has been disaggregated, but its CPU and memory are still coupled. Memory capacity will be limited by the single physical machine's memory capacity, and the memory can only be expanded with the CPU specifications. The problem of fate shoring must be also figured out. The failure of one resource, for example, the CPU, will cause the failure of other resources, for example, the memory. And at last, the redundant in-memory state copies must be figured out. Whenever the monolithic machine or the shared storage architecture, the memory are all parent, so they all have multiple copies of a single date. And next, we will talk about the serverless database service. Recently, many cloud vendors have provided database serverless service on the basis of the cloud-native database. The main design goal is to on-demand resource provision, which enable elegant resource adjustment according to the actual workload, and provide a pay-as-you-go payment model. However, the current serverless database based on the specification of the storage and the computing have several obvious limitations, which affect the user's experience and resource utilization. First of all, is the problem of the resource coupling. The current minimized scale unit of the serverless database is a couple of CPU and memory resources. For example, one virtual CPU plus 2 GB memory. And the second problem is the fast resume after auto pause. Because currently CPU and memory are released together after auto pause, it can't only release the CPU, which will take a long time to fulfill the big buffer pool in the memory. And finally, when the auto-scaling needs to cross physical machine, because the transaction information in the memory can't be synchronized, transparent scaling are difficult to achieve. Earlier, we talked about the current limitation and the challenges of the cross database, especially the serverless database service. So let's discuss our solutions. In this paper, we proposed a novel disaggregated cognitive database architecture as shown in the right side. It goes one step further than the shared storage architecture to address the aforementioned problem. So first, you can see that the PolarDB serverless is a fully disaggregated architecture. The disaggregation architecture runs in the disaggregated data center, in which the CPU, memory, and storage resources are no longer tightly coupled. Resources are located in different nodes connected through the high-speed network. And secondly, because of the disaggregated architecture, memory can, memory can support horizontal scaling across physical machine independent from the CPU. And finally, based on the disaggregation memory's feature of cross-node cache coherency and transaction consistency, multiple nodes can share the same data copy in the disaggregated memory. This can help us to overcome the redundant in-memory copy limitation in the former architecture and make the access of the RO node state strong consistent with the RW nodes. The disaggregated memory component is a newly introduced component in the PolarDB serverless compared to the PolarDB. This is a distributed memory cluster across multiple physical machines. It is a new remote memory access interface to access the disaggregated memory. This memory cluster is composite of home node, sub node, and the local cache in the CPU node. The home node stores the meta information of the entire memory cluster and the latching information of the database. The sub node is used to storage memory data pages. The local cache is a high-speed cache located in the CPU node. It designs and implements cross-node cache consistency mechanism and transaction consistency mechanism to let the CPU node share the same data copy in the disaggregated memory. We use the cache invalidation to achieve cache consistency between nodes. Here is an example of cache invalidation. When the RW nodes finish modifying some page and before he releases the page ledge, first he will set the local pages invalidate bit we call it PIB. Then RW node will send the page validation API call to the home node. Once when the home node receives the API call, we will first set the local PIB in the home node, and then he will obtain the corresponding RO copy information of the page from the page reference directory. We call it PIB. The stamp 5 and the stamp 6 represent the process of the RDMA remote write to set the PIB of the RO node to invalidation the page copy in the RO node. And the stamp 7 and the stamp 8 represent the result returned to the RW node finally. This picture shows the mechanism of the cross-node B plus tree consistency. We use the global physical latch to achieve the automatic access to the stamp page located in different nodes and ensure the structural consistency of the B plus tree. And we use the thickness policy to reduce the access frequency of the page latch located in the home node to optimize the locking latency. And we also adopted the fast-pass mechanism based on the RDMA to improve the communication latency in no complicated scenarios. PolarDB serverless provides snapshot isolation based on MVCC. In PolarDB serverless, transactions rely on a snapshot timestamp to control which version of record the transaction is allowed to see. It maintains a centralized timestamp named CTS in the RW node. CTS represents the commit time of a transaction or the query time of a read view. When a read-write transaction begins, it will first reserve the slot in the CTS log. And when the transaction commits, we will first obtain a new CTS from the CTS source and fill it into the CTS log. And then we will start a asynchronous task to fill the CTS into the record. When the RW node starts a read query, it will obtain the CTS directly from the CTS source of the RW node to create the read view. And then when he reads a record, he will compare the CTS in the read view to the CTS in the record to check the visibility of the record. And if the RO node finds that the CTS in the record are not filled, it will directly send a RDMA remote read to the RW node's CTS log to get the corresponding CTS of this record. Page materialization uploading is also an important design point of the PolarDB serverless. As we know, the transaction on monolithic database will theoretically flash data page to the durable storage. However, it will introduce a large amount of network communication between the RW node, the RO node, and the disaggregation memory, and with the PolarFSE, PolarDB serverless. Therefore, we adopted the idea of log as a database. We expanded the capability of the PolarFS. Now, in the PolarDB serverless, PolarFS can generate new pages by replying the result to the baseline page instead of flash data page from memory to the PolarFS. This design saves a lot of network communication between the RW node, the disaggregation memory, and the PolarFS. The last important design point of the PolarDB serverless is the transparent auto scaling. The capability of transparent auto scaling without interrupting customers' workload is very important for serverless database. In PolarDB serverless, when scaling event happens, the proxy node is responsible for keeping the client's connection alive. The old RW node first synchronized a small amount of data page into the disaggregated memory and save the transaction information and save quality into the disaggregation memory of the long-running transaction. After switch to the new RW node, these long-running transactions can be rebooted and continue. And because most of the cached pages are still in the disaggregated memory, the database throughput can be resumed immediately. The entire switch time is only about 2 or 3 milliseconds, and the user will not experience any disconnections or abort transactions. The evolution of the disaggregated architecture could have a negative impact on the database performance, since data is likely to access from the remote memory or the remote storage node. involving notable network latency. To address this problem, we employ two major optimizations to minimize the chance of the compromise. The first one is because our RW node is only for snapshot read. We introduce optimization based on optimistic locking. We use a SMO version to detect if the SMO happened in the RW node. Only when the RW nodes have SMO, the our node will add the global page legend. And the second one is the index over perfection. We implement a current perfection mechanism by loading data pages of the other index that will be accessed later. Finally, based on the above design, let's take a look at the benchmark result of the PolarDB service. First, we compare the performance of the PolarDB and the PolarDB service with a very local cache size in the most popular OLTP benchmarking industry. That's Sysbench and TPCC. The results shows that the PolarDB serverless throughput is very close to the PolarDB in most OLTP scenarios. In the most extreme scenario, with smallest local cache size, that is half gigabyte, the throughput drop is about 13% to the 18%. We also evaluated the performance of PolarDB serverless and the analytical workload, that's the DPCH, because the analytical query needed to access a large amount of remote memory. The performance degradation is relatively observed, up to about 50%. 40%. Although the PolarDB serverless has obvious degradation in the analytical scenario of DPCH, we can strengthen the performance of analytical scenario by scale out the memory capacity. The above figure shows the throughput of PolarDB serverless while scaling out or scaling in the remote memory. We can see that with the expansion of memory capacity, the throughput of DPCH has increased rapidly. Also, because of the CPU and the memory are separated, their fate are no longer shared. When the CPU nodes fail, the disaggregated memory still survive and maintain most of the memory state. So the new CPU can take over very rapidly. That's all I want to talk today. Any discussion of PolarDB subjects or relative is welcome. Don't hesitate to send a message to me. Thank you for your time. Bye bye.